Okay, Bob, not yet. I'm going to introduce you. That's not an introduction.
I should have a laser pointer in your eye.
Right. This is all, so you're taking me all the way back to when we first got here in 1990, and you missed your first class because you left your car parked out in the main street out there because you were late.
Yeah.
Gary was Bob's second cosmology hire, and we used to live over on the roach-infested 4th floor of Smith Lab. It's probably still roach-infested. And I think you got here in 1989-ish or so. And I first met Bob and Gary at almost the same time at Fermilab. Bob was easy to spot because when he would come and visit his advisor, Mike Turner, he would wear, for some reason that I still don't understand, kind of an Oktoberfest hat with a feather out of it. No lederhosen, but for some reason you wore that hat. And that's how I first met you, because I said, who is that guy with the hat? Today, Bob is a science fiction writer of some repute, right?
Yeah.
I think is, yeah.
But now you're talking about the cosmology papers or the science?
So now I won't use that joke. In his spare time, he was the chair of the Vanderbilt Physics Department for 13 years. He just gave that up, but not the uniform. And he's a card-carrying cosmologist. One of Gary and Bob's shared interests was Relic Abundances of particles left over from the Big Bang, and that's what he's going to talk to us about today. Thanks, Bob.
I'm going to talk about Gary's work on relic particle abundances. It's probably not the thing he's the most well-known for, but I wanted to highlight it for 3 reasons. One is that I think it is really significant and sometimes underappreciated. Secondly, it's an area where my own interest and his kind of overlapped and came together at various times in our careers and lives. And thirdly, I've been looking at some ideas of his from about 50 years ago to see if I could get some new stuff out of them. And I'll talk about that at the very end of the talk. Gary really got in on the ground floor. I think we tend to forget that. But cosmology began, essentially, modern cosmology began in 1965 with the discovery of the cosmic microwave background, which led to essentially the development of the hot Big Bang model. It cemented the hot Big Bang model as the correct model of the universe. And Gary wrote his PhD only 3 years later on matter-antimatter interactions. And I want to highlight that because I think that planted the seeds of a lot of his later work, both his work on relic particle abundances and I think his interest in Big Bang nucleosynthesis grew out of this question of whether there were equal amounts of matter and antimatter in the universe or whether the matter was more abundant, which we know to be the case. And in fact, he wrote a very important paper in 1969 in Nature, which was only his 4th paper. That's not a bad track record to be, one of your very first papers to be in Nature, on the excess of matter over antimatter in the universe. And then a very influential review paper just a few years later where he summarized a lot of his work on the excess of matter over antimatter. So if the universe were matter-antimatter symmetric, there's a lot of things we would see. And this is a summary of Gary's arguments. We would get photons from annihilations in the interstellar medium of baryons and antibaryons annihilating. You'd see a lot of antinuclei in cosmic rays. And then on larger scales, you would see gamma rays from annihilations in galaxy clusters. And so the absence of all of these things puts very strong upper limits on the amount of antimatter in the universe. And as Terry said, Gary was very, Gary was very methodical and very detail-oriented and didn't compromise when he was going after things. And so his work in this area really shows those characteristics. John, did you have a question?
Yeah, can you just make sure the microphone's on for the capture?
It's probably, it says power on.
Okay.
So it's on. Okay. And in fact, Gary came back to this work later in his career. In 2008, he wrote a paper on the famous bullet cluster. This is a colliding cluster of galaxies with, which has been used to constrain a lot of things in cosmology. And he showed that this constrains the antimatter fraction to be less than about 3 × 10⁻⁶. So the basic conclusion to come out of all of this work that Gary did is that there's an excess of matter over antimatter. There's very, very little antimatter in the universe today, and there's a lot of matter. So then the obvious question is, where did this come from? Well, one thing you could do is just put it in as an initial condition, but that's not a very satisfying way to do cosmology. So the other question is, could we start off with an initial symmetry of matter and antimatter, and could that lead to a baryon excess later? And this, I think, led to Gary's interest in relic particle abundances. So there was earlier work in this field by Zeldovich and Chu, but imagine you have a bunch of matter and antimatter. So you probably don't realize this, but baryons are black and antibaryons are white. And they're bouncing around and colliding with each other. And as they do that, they annihilate. So you can see that, there's not as many left. And you can write down an equation that describes the evolution of these particles. So if n is the number density of baryons, the time derivative of it, first of all, there's a term that's just due to the dilution from the expansion of the universe. As the universe expands, the density goes down, and we eventually change variables to get rid of that term. But then there's a cross-section, and the annihilation rate is proportional to the cross-section, average cross-section velocity times the number density of particles squared. And then there's a creation rate for these particles, and that's very complicated because you have the thermal background and everything's annihilating to create particles, but there's a trick you pull out of your hat, which is you use detail balance. When things are in equilibrium, the annihilation rate and the creation rate have to equal each other. That's from the mysterious area called thermodynamics that none of us really understand, right, Terry?
Still working on it.
I am too. So if you simply set the creation rate is just the negative of the annihilation rate in equilibrium, and that gives you this creation term, the equilibrium number density squared. And you can integrate this equation for the case of an initial baryon, anti-baryon symmetric universe. And what you find out is that the annihilations are incredibly efficient, and you get almost no nucleons left. So if you want to start off with an initial baryon, anti-baryon symmetric universe, you get a ratio of nucleons to photons at the end of about 1 part in 10 to the 19. And what we actually observe for our relic abundance of baryons is 10 to the minus 10. And the other thing that's wrong with this calculation is you would get equal numbers up here of baryons and antibaryons, which we don't see. Now, this gave rise to an entire new field in cosmology called baryogenesis. How do you start off with a baryon-antibaryon symmetric universe and then end up with one that has more baryons than antibaryons? And I'm not going to go into detail on that, but it really remains a bit of an unsolved problem. And we have, as usual in cosmology, we have a lot of solutions, but we don't have one solution. We're still discussing what the best way is to do that. But essentially what Gary showed is that you need an excess of nucleons over antinucleons initially, and then as they annihilate down, you end up with what we see today, which are the nucleons. And Gary wrote a very influential paper in 1979 in which he discussed in detail the Boltzmann equation. That was the equation I showed you a few slides ago. And he talked about how you would solve the Boltzmann equation, not just for the case of baryons, but for the case of an arbitrary particle. So I think it's clear that the intellectual history of this idea is he got interested in the baryon abundance. He looked at a lot of these equations for the evolution of particles, and then he realized, as did other people, that you could apply this to other particles. So he wrote this very influential paper where he talked about the evolution of arbitrary particles. This was in the 1970s. And this is where I first, in a sense, met Gary. I didn't meet Gary in 1979, but I first read his papers in 1979. I was a senior at Princeton doing a senior thesis with Jim Peebles, who kind of knew this stuff and kind of didn't. It was on massive neutrinos. And I didn't understand why it was that if you had light neutrinos, the density simply goes up with the neutrino mass because they're relativistic. But for massive neutrinos, it goes down again because they start to annihilate. And then I encountered Gary's paper, his 1979 paper, and read the paper, and it was clear to me. And I've remembered it ever since then. Now, this is me in 1979. This is my class of physics majors at Princeton. You'll never see a more motley crew, and that's me. I'm here. Now, I think the takeaway from this part of the talk is if there are any photos of you from the 1970s, when you go home tonight, find them and destroy them, because none of us looked good in the 70s. So these twins here are billionaires. They work at the Simons hedge fund, and don't answer my emails anymore. He's, I think, a multimillionaire. These guys went into finance. The rest of us failed and went into physics. But I remember very, very clearly reading this paper in 1979 by this Steigman guy and sort of, I think, understanding what he was talking about. So let me talk about that in a little more detail. Imagine that you have some arbitrary particle. So we're not talking about nucleons anymore necessarily. This is any massive particle. And it can annihilate into electrons and positrons or photons or any other thermal particle. And you can then use this equation to trace the evolution of the particle with time. And in Gary's paper, he used this variable x, which was the mass of the particle divided by the temperature, which has the advantage that temperature goes down to the right. So time goes to the right, as it does in most graphs. And this is the number density of the particle times a fixed volume. So here he's getting rid of the dilution effect due to the expansion of the universe. If you look at if you allow the volume to go up and the number density to go down, the number of particles stays the same if they're not annihilating. And if you have a relativistic particle, this quantity is simply constant, and it tracks this horizontal line here. If the particle becomes non-relativistic, initially the particle simply tracks its equilibrium abundance. So when you set n equal to the equilibrium abundance, as long as this number is very, very high, this will track very, very closely to the equilibrium abundance. And recall that if you have a massive particle, the equilibrium abundance goes down exponentially as e to the minus mass over temperature. So a particle that's in thermal equilibrium simply goes down and down and down and down and down, and that's all it ever did. It would be essentially annihilated away to nothing. But what happens is at some point, this rate gets too small to keep the particles in thermal equilibrium, and they gradually approach a constant abundance per co-moving volume. And this constant abundance is called the Freezeout Abundance. So this process in which the number density of the particle eventually reaches a constant per co-moving volume is called freezeout. And this was the key calculation, I think, in this paper, where you have this Relic abundance. And of course, the main interest in this today is not the baryon abundance, but the dark matter abundance. We think there's a dark matter particle, and the one way that the dark matter particle's abundance can be achieved is by assuming that it obeys this Boltzmann equation and then calculating the Relic abundance of the particle. Now, after I left Princeton, I was in England for a couple of years on vacation, courtesy of the Marshall Fund, and then I came back to do graduate studies, and I joined the Chicago Mafia in 1983. So for those of you who are not in the field, the Chicago Mafia is a sort of term of endearment, I think, to describe the cosmology group that grew up around David Schramm and Mike Turner and Rocky Kolb in the 1980s. And we used to have these really nice pizza lunches where people would get together and order deep dish pizza. Gary was, now those of you under the age of 50, this is a famous movie, but anybody recognize? Gary was never really, I think, a part of the Chicago Mafia in the sense that he was never based at the University of Chicago, but he formed a kind of indispensable collaborator. And so I would compare him to Tom Hagen, the consigliere of the Corleone family. So he would come and work with people and then go back to Bartol and then come back and work with people and go back. And so he played a major role in developing the cosmology within the Chicago group. I joined the Chicago Mafia and ended up working with Mike Turner, who's up here in the front row. When I showed up at Chicago, I didn't really know much about cosmology, and Mike didn't know much about programming computers, so it was easy for me to convince him that I did know something about programming computers and stayed one step ahead of him. And then we worked on this same problem, which was the Relic Abundance problem, and wrote this paper in 1986. So I should say 1983, when I got to Chicago as a grad student, that's when I first met Gary, because he was kind of always coming and going. And I met him in that very first fall when I arrived in 1983, although I didn't get to know him very well that year. So Mike and I refined the calculation, and the only thing I want you to take away from this, because I'm going to refer to it later in the talk, is that we derived an expression. This was a sort of improved way of talking about the number density per co-moving volume. We take the number density relative to the entropy density, which also expands with the volume. And you get this Freezeout Abundance, which essentially scales as 1 over the mass of the particle times the cross-section, annihilation cross-section. But when you want to get the mass density today, you have to calculate that, multiply this number density times the mass of the particle. So the mass density, the contribution to the critical density due to the dark matter, the mass mostly scales out of it, and you get something that really just goes as 1 over the cross-section. And the cross-section you need to get dark matter today is a sigma v of about 3 times 10 to the minus 26. And I wanted to bring that in because I'm going to talk about it a little bit later in the talk today. So that's where my interest overlapped with Gary's in this relic abundance calculation. And 1986 was also the year that Mike sent me at the very end of my graduate career to Aspen, where I met Gary again. And there was also this, I'm not really an outdoor person. All those of you who know me know that I'm not an outdoor person. I mean, I sort of tolerated Aspen and the beauty and the mountains and everything, but I wasn't really into it. But I especially don't like dogs. And I was appalled that there was this gigantic stray dog wandering around the grounds, and I figured he probably had rabies. He's going to bite me. And then I was relieved to discover that the dog had an owner who was, this was, of course, this picture is a bit before 1986, but he had an owner who was Gary. And I talked to Gary a bit in 1986, and I said, well, I heard you're moving to Ohio State. And he said, yeah, we should talk about that later. And I never did talk with him about it, so that shows I wasn't really on top of the job search at that point. But destiny brought me to Ohio State anyway. So that was my sort of second big encounter with Gary was at Aspen, and of course he was a perennial Aspenite. And then in 1989, Gary actually did bring me to Ohio State, so I joined the Ohio State Mafia, which is not as well organized as the Chicago Mafia. Some of you remember this. This was our Don DeLucia, who ran the department for several years with a heavy hand. And this was, some of these people aren't here anymore. This was Bob Scherrer. I was Don Ken, and Bill Palmer was Whitey. And I don't know if you knew, and John Whitcomb, I don't know what became of him, was the unwelcome guest. But I joined the group here. And at that point, ironically, Gary's interest and mine diverged a bit. So Gary mostly at that point was working on Big Bang Nucleosynthesis, which Keith is going to talk about in a little while. I actually drifted into large-scale structure for a while, but then I got over it. And went back into physics. But Gary and I wrote a few papers together with a number of other people who are in the room. This was our collaboration during my time at Ohio State. And Terry was on quite a few of these papers, actually nearly all of them in my time here. Of these papers, they cover the gamut. Most of them are BBN papers. There's a few on dark energy. The most influential one was this BBN in crisis paper, which has the distinction of being the only paper I've ever been on in which the referee micromanaged the punctuation. So we wrote Big Bang Nucleosynthesis in Crisis, and the referee made us add a question mark to it, which rankled Gary, I think, for a long, long time. And so I'm going to on this conference in his honor, I'm going to correct that. And so this one's for you, Gary. The Big Bang nucleosynthesis, I think Big Bang nucleosynthesis does have issues with lithium, but it wasn't the issues we were talking about in 1995. But it doesn't matter. The question mark's gone. So in 2003, I left Ohio State, as you noted, to join the Vanderbilt Mafia, which was a little bit less threatening than everyone under the age of 70 doesn't know what that is. But I joined the Vanderbilt Mafia. And this guy, by the way, went on to play Superman in the TV series. And at that point, oddly enough, or ironically, I think Gary and I both came back to the study of relic abundances. It's something that just won't go away, and it continues to be an interesting question. So my first paper on this that I wrote had to do with Sommerfeld enhanced interaction. So in the Sommerfeld, when you have a Sommerfeld enhancement in the annihilations, this is yet another variation on dark matter, you get a 1 over V enhancement in the annihilation rate. You have a long-range force, and it enhances the annihilation rate at low velocities, which was considered desirable for various reasons. And we did a calculation of this to get the relic abundance. And we discovered that you could treat this with the standard formalism, but you have to be very careful about kinetic decoupling. That is, when does it stop scattering off the background particles as opposed to when it stops annihilating. So that was my paper that I wrote after I left here. And then Gary wrote a very detailed paper with John Beacom, who's in the audience, where they re-examined the entire issue of the relic abundance of these particles. And I think this illustrates Gary's tenacity, because when he was writing this particle, he sent me a whole bunch of notes and said, Bob, I don't think this is right, and I'm not sure that's right. And he was a real bulldog when it came to details and really ferreting out the truth. And so he was like, do you think this is correct? And what about what about this calculation? And I was like, oh, Gary, whatever, because I was more of a chihuahua than a bulldog as far as getting to the bottom of these things. But he ran this to ground and did a much more detailed calculation of the abundance of these particles. And in particular, what he did was an improved treatment of the number of particles in thermal equilibrium. And the reason that's important is that affects how fast the universe is expanding. The more particles you have in thermal equilibrium, the faster it expands. And it changes the relation between the temperature of the universe, of the thermal background, and the time. And that affects the freezeout abundances. And so the final result that Gary and John and I don't know Dasgupta, is he here? No, not here. He was a postdoc. Does he? Okay, he left Ohio. But what they discovered is that if you do the calculation more carefully, at large dark matter masses, you actually get an abundance which is a bit lower than the canonical 3 times 10 to the minus 26. So this is the canonical abundance that we were all using. For large masses, it's closer to 2.2 times 10 to the minus 26. Now that might seem, in cosmology, what's a factor of 1.5? But we've got these direct detection experiments that are going to hopefully see something eventually, and you want to know what cross section you're looking for. And then at smaller masses, you get a change in this cross section that makes it actually a bit higher than the standard. It's almost double the standard. So I think this was a very important calculation, and it has become kind of the most recent standard freeze-out calculation that people have tended to cite in their when they need a calculation of the relic abundance. And Gary's last refereed paper was continuing almost back to his original work, because he was looking at CMB constraints from thermal WIMP annihilation. So to go back to this picture, remember that initially these particles are annihilating and being created, and at late times they're freezing out, but there's this residual annihilation. You can see that these curves continue to go down even to very late times. And this residual annihilation dumps energy into the cosmic microwave background, and that's something that a number of people in this room have looked at in some detail. Gary was looking at limits in which the dark matter doesn't provide all of these particles don't provide all of the dark matter, and looking at what kind of limits you can put on the cross sections in that case. And so that was, even at the very end, he was interested in this question of relic particle annihilations. Now, the last thing I want to talk about is some ideas I've been batting around lately, and they may never get anywhere, but I think it's interesting because they go back actually to Gary's 1969 paper. And that is, what about statistical fluctuations? Could that give you the correct relic abundance of nucleons? And the answer is no. The idea is, of course, in a thermal distribution, you always have root n fluctuations. And so you're going to have regions of space with a slight excess of baryons, just square root of n of the number of particles there, and other regions with excess of antibaryons, and they're limited. The volume at best is limited by the causal volume, the velocity times the age of the universe. And then you can ask, well, do you get a relic abundance of particles that's interesting? And the answer is no. These relic abundances are about 10 to the minus 44. And this is an ancient idea in cosmology. There aren't that many ancient ideas, but the farthest back I could trace this was Alpher, Fowlin, and Herman in 1953. So that was before many of us were born. It was, in fact, when Gary was 12 years old, so he wasn't working in cosmology back then either. But they talk about this these root end fluctuations. And then a couple of people looked at them not in connection with particle abundances, but other kinds of fluctuations, root end fluctuations in cosmology. Kolben-Turner in 1982, and then Grice, Kolben, Maserati in 1989. So what I wanted to do after I was looking at Gary's paper was to revisit this question, see if there were any extreme conditions where this might be interesting. And so far the answer is no, but I think that it gets close to something that might be interesting. So I'll call this diffusion-limited freeze-out. Remember, your particles are not only annihilating, they're also scattering off the thermal background. And this is something that Mark Kamienkowski explored about 15 years ago. And you can calculate their mean free path, and you can calculate their diffusion length. They just do a random walk with a mean free path times the velocity times the time. And if they freeze out to such a low abundance that their mean free path, the number of particles inside a diffusion length is less than 1, you get a very different freeze-out calculation. And so you can do a back-of-the-envelope calculation and see that this actually becomes relevant for a mass of about 10 to the 4th TeV. Now, that's not insane. The problem with it is that it violates what's called unitarity. You can actually, there's an upper bound on how heavy the mass can be, which is about 100 TeV, which is also due to Mark. And so this is not, at this point, an interesting, well, it's not a publishable idea, even by University of Chicago standards. But it might, we're looking at, and by the way, I'm doing this in collaboration with Richard Galvez, who's a postdoc at NYU. I'm looking at other scenarios, asymmetric freeze-out. I mean, certainly if you could artificially increase the scattering cross-section, you could make this interesting. But the scattering cross-section should be at about the same order of magnitude as the annihilation cross-section. So it would require some really bizarre models to make this work. But I'm playing around with this, and I bring it out just because, as I said, I kind of got interested in it, and because it goes back to Gary's very, very first paper, or his fourth paper, which he wrote in 1969. So there are no obsolete ideas in cosmology. They're just ideas that haven't quite been fully exploited. And I'm taking another look at this. So ironically, I think Gary came back to this question of freeze out at the end of his life, and I'm doing the same thing. Hopefully, not at the end of my life, but the more recent epoch in my life. Gary was also an inveterate. He got to every conference, and this is the Solvay conference of 1927. You can see he's back there, and he's listed with Pauli and Heisenberg and Scherrer. I think this is where he would have wanted to be. Gary made a big impact in my life. He brought me to Ohio State, and I met my wife here. I had a bunch of kids. None of them would have existed if it hadn't been for Gary. I've got 2 kids now that have both published physics papers, and so Gary can take credit for those as well. And our lives touch each other in ways we never even dreamed of. And I think in Gary's case, it was a very positive impact on all those that he worked with. So thank you.
Thanks, Bob. Does anybody have any questions for Professor Scherrer?
Yeah, Mike.
I thought you did a great job of capturing Gary's scientific essence. But I had a question about the Relic Abundance calculation.
Uh-huh.
So you've got particles that freeze out during the transition from